have to consider individual pressure and temperature. When we are taking the pressure, we have to take at constant temperature and vice versa. So let us say effect of pressure at constant temperature. So now we have studied that pressure leaked upon time. More the pressure, more is the rate. So obviously rate is directly proportional to the pressure, and this is something what we know already, upon D or upon square root of M. Either you write 1 upon square root of D or 1 upon square root of M. So when we are combining these both of these, so for gases G1 and G2, what do we have? R1 upon R2 equal to P1 upon P2 multiplied by M2 by M1 square root. We are just combining. So when the pressure is different, so pressure will come into action. And what will be the pressure? What will be the role of the pressure? The pressure will be multiplied, because pressure is directly proportional. You apply more the pressure on a balloon, the gas will come outside with more speed, that is more rate. So pressure leaked upon the time taken, you can say the time is consistent. So we are taking P1 by P2 M2 by M1 square root. Now what will happen if the temperature is different but the pressure is constant? At different temperatures, we are taking the ratio of the rates of two gases. So the rate is directly proportional to the square root of temperature. That is rate, we are writing it, that is rate R is directly proportional to square root of temperature. So if this rate is directly proportional to square root of temperature, so it can be written as R1 by R2 equal to T1 T2 square root and multiplied by D2 by D1. This is something we already know from here, isn't it? So T1 by T2 and M2 by M1 combined square root, that is T1 M2 upon T2 M1 square root, that is the ratio of the rates of two different gases. Now let us come to a conclusion. What is the uses of Graham's law of diffusion or effusion? So when we are taking the uses, there is one isotope called uranium, and when uranium is combined with fluorine, it makes UF6. It is gaseous isotope, it is gaseous molecule. So the uranium has two isotopes. Now you would say, where is the isotope? Uranium has 235 and 238. So UF6 235 and UF6 238, there will be two isotopes, gaseous molecule. They can be separated because both of them will be having different molecular mass and different densities. So we can separate them, and this is the process. How do we separate the 238 uranium from 235? And that is something, the way through which nuclear proliferation, that is the isolation of two different isotopes of uranium, is being done by connecting them, reacting them with fluorine, making UF6, and then 235 and 238 uranium are isolated because now they become the gases. So density and molar mass is also known. This can also be known from where? By using Graham's law of diffusion. That is something very easy thing, because we have studied the formulae, and by knowing the rates we can know the density, and if we know the density we can know the molar mass, isn't it? And obviously the gases can be separated. One gas will be diffusing slowly in comparison to other gas. This way we can separate two gases by using Graham's law of diffusion. This is the practical applicability, right? So now if a gas, there is something very important thing. Now let us say there is a very fine, very slick tube, and a gas is entering. So obviously let us say it is traveling a distance d1, and one gas is coming from here, it is traveling a distance d2, right? So obviously let us say the d1 distance, obviously this combined is d1 plus d2. So if a gas travels d1 distance with the rate r1 and it is meeting, let us say, at some point here, it is meeting at some point here, so obviously because we have studied R1 equal to D1 upon time and R2 equal to D2 upon time. So meeting means the time is same, isn't it, from here to here. And let us say the gas started from here and it reached here, and the gas started from here and reached here at the same time. They are meeting at some point. So what will happen, because the time is same, so what we can say, R1 upon R2 equal to D1 upon T1 upon D2 upon T1. So T1 will eventually cancel. So R1 upon R2, that is rate, speed, is equal to distance upon time, because the time was same. So that eventually cancelled out. So R1 upon R2 equal to D1 upon D2. So for analytical purpose, what we can do, we can write +1 and +1 both side, and we can do the manipulation as if required, as and when required, right? So if a gas travels a distance d1 with rate r1, meets other gas which has traveled distance d2 with r2, then obviously r1 upon r2 equal to d1 upon d2. So now let us do a quick revision, and then we will solve few numericals, few good numericals right from the basics, covering each and every concept. So we know when two gases are intermixing, what happens? No external energy is required. But if effusion happens, external energy is required. If effusion happens, then after effusion, diffusion will certainly happen. Then there is Graham's law of diffusion and effusion. Rate is inversely proportional to square root of density, directly proportional to V by T, directly proportional to pressure leak by T, and that happens at constant pressure and temperature. And then what do we have? We have, if the pressure is constant and if the temperature is constant and pressure is different, then we have R1 upon R2 equal to P1 by P2 multiplied by square root of M2 by M1. Similarly, at constant pressure, what do we have? The temperature is different if R is inversely proportional to square root of temperature T1 M2 upon T2 M1. So these are basic formulae we have studied. So now we are taking question. So you don't have to see the solution. I am just hiding the solution for the sake of it. You don't have to look the solution. Please don't look the solution. So you have to pause so that you can solve the question by yourself, and once you give up, you can see the solution. Dear students, the most important thing about solving a question, is never ever look the solution. Try to read the question, analyze it, and never ever look the solution. So let us read the question. The relative densities of oxygen and carbon dioxide are 16 and 22. If 25 centimeter cube of CO2 effuses out in 75 seconds, what volume of oxygen will effuse out in 96 seconds under similar conditions? So look at this question. First of all, volume V1 T1 and V2 is not given, but T2 is given. And what is given? D1 upon D2. And what is asked? What volume? So we have studied this one. Look, volume is given, one volume is given, time is given, densities are given, only V2 is not given. So we can directly use the formula, that is V oxygen multiplied by, obviously this was in denominator 72, V1 T2 multiplied by V2 T1 equal to D2 by D1. So it is obviously 22 and 16 square root, this comes out to be 1.17, and obviously this is 1.17, and then 25 will multiply, that is 1.17 multiplied by 25 upon 75 and multiplied by 96. This way it comes out to be 37.5 centimeter cube. This was the easy question. Now in a single question we have studied all the formulae. So we will take a little bit analytical question, right? You can read. What if you don't understand